Hi everyone, today we're going to talk about probability, mostly a review of Stat 230. Before we start, I want you to think about what you remember from the first few chapters of Stat 230. Maybe jot some notes down, maybe pull open your notes if you have them, but we'll go through the basic definitions and talk about the various axioms of probability and some probability rules. So first of all, for the definitions, we have an experiment, which is any process that can be repeated a number of times with a number of different possible results. And the key is it can be repeated over and over again. A trial is what we call one iteration of an experiment. An outcome is any one of the possible things that can happen on one trial of an experiment. And then finally, we have the sample space, which is a set of all possible outcomes that can occur on one trial of an experiment. And now a few things about sample spaces. They have to be considered to satisfy these properties. We can't have anything left out. So every outcome has to be in the sample space at least once. And we also can't double count anything. So that means there can't be, the same outcome can't be in the sample space more than once. The order doesn't matter because it's a set, and it could be a discrete sample space, which is if the set is finite or countable, or continuous if the set is uncountable. Here's an example of a sample space. The experiment might be rolling a fair six-sided die repeatedly over and over again, and a logical sample space would be the set of numbers 1, 2, 3, 4, 5, 6. But that's not the only one. We could have the sample space be odd numbers or even numbers. We could have it be prime numbers, composite numbers, or 1. Or even, 5 or not 5. There's lots of different possible sample spaces that satisfy it. Inside a sample space, we have an event, which is a subset of the sample space. And it could include the empty set or the entire sample space. Actually, it doesn't have to be a proper subset. And we would say that the event E occurs on a trial if the outcome on that trial happens to be a member of that set E. So returning to our example, let's define some event E to be that the roll is greater than 2. So E would consist of the elements 3, 4, 5, and 6. And another event F might be that the roll is even, then F would consist of the elements 2, 4, and 6. We can see then if the outcome that happens on a single roll of the die is 4 or 6, then both E and F would occur. If the outcome is 2, then only F would occur, not E. If it's 1, actually neither of them occur, and if it's 3 or 5, then only E would occur. Finally, some other definitions. If an event only has one element in it, we call it a simple event. Otherwise, it's known as a compound event. And you can see that compound events are just combinations of simple events. Once we have events, we can't add or subtract them. We have to use set operators. And we have 3 set operators. First of all, union. E union F is everything in E or F or both. E intersect F, or just EF, is everything that's in both E and F, and E complement, or E bar, is everything that's still in the sample space, but not in the event E. So we can actually illustrate these things with Venn diagrams. So here's a diagram of the sets E and F within a sample space S. The shaded region is E union F. Here again, we have E and F, and the intersection there is EF. And finally, if we have E and F, then everything outside of E, whether or not it's in F, is E complement. Here's an example then. Taking our same events from before, E union F would be everything that's either greater than 2 or even, or both, so 2, 3, 4, 5, 6. The intersection is only 4 and 6, and E complement would be 1 or 2. Couple of relationships between events. If 2 events have no elements in common, in other words, the intersection of those 2 events is the empty set, we say that those elements are mutually exclusive. On the other hand, and something that's often confused with that, is if 2 events have no influence on each other, then we say that those events are independent. And I want you to take a second and think about what is the difference between mutually exclusive and independent. So take a second and think about the difference between those 2 things. All right. Next, we are able to define the idea of probability. A probability, or a probability measure, P, takes events in a sample space, S, and then maps them to real numbers. But it does it in a way that's subject to 3 axioms. The first axiom is that no probability can be negative. So no matter what the event is, it has to be greater than or equal to 0. The probability of the entire sample space is 1, and if E and F are mutually exclusive, then the probability of the union is equal to the sum of those two probabilities. That third axiom actually has a name. It's called the additivity axiom, and these three components are actually not provable. You can't prove axioms. They're things you have to assume, and then everything else is going to follow from them. So we might have other properties of probabilities that make logical sense, and all of them can be derived directly from these three axioms. So one that you might be aware of is that the probability of E complement is 1 minus the probability of E, or the probability of E union F is the probability of E plus F minus that intersection. Or finally, if F is contained in or equal to E, then the probability of F is less than or equal to the probability of E. See if you can try to prove each of these three relatively obvious results, but only using those three axioms of probability. And spoiler alert, the additivity axiom is going to be used in all three of those cases. So give that a try. See if you can prove those three things just from the axioms. All right. Next, I want to talk about conditional probability. So if we know some event has occurred, we might be interested in knowing how that changes the probability of another event. So we define the conditional probability of F given E as the probability of E and F divided by the probability of E, provided that the probability of E is not 0, because we can't divide by 0. Well, for an explanation of why that is, I want to think about how we can arrive at this. So here's E and F. And if we know for sure that E has occurred, we're going to kind of erase the rest of reality, and only what's in E is now the possible things. And then the only way for F to also occur is if we end up in that intersection, E and F. So looking at this new E as the new sample space, the probability of F happening, knowing that E has happened, is the probability that they both happen divided by the probability of E. So hopefully that explanation makes a little bit of sense. Another neat thing we can do is rearrange this definition, just multiply on both sides by P of E, and we get the probability of E and F is P of E times P of F given E. And we could rearrange it in the other direction. We could get that P of EF is equal to P of F times P of E given F. So both of these are two different ways to arrive at the probability of that intersection. And we sometimes call this the product rule. Now we're ready to define independence formally. We can say that E and F are independent events if and only if the probability of the intersection, E and F, is equal to the product of those two probabilities. But an equivalent definition is to think about it from the perspective of the conditional probability. If the probability of F given E is equal to the probability of F, and the probability of E given F is equal to the probability of E, that's telling us that knowing one event has occurred tells us nothing about the other event. So that definition is equivalent if you just sub in the definition of independence to the definition of the conditional probability. Returning to our previous example, we had our event E being the values 3, 4, 5, and 6, and F was 2, 4, and 6. So we might be interested in whether these two events are independent or not. To do that, we have to figure out what their probabilities are, and by the axioms of probability, the probability assigned to each one of those 6 possible outcomes is 1/6, because remember, axiom 2 says that the probability of the entire sample space is 1. And this is a fair die, so each of the 6 outcomes will have 1/6 probability. So that means P of E is just the sum of the probabilities of each of those points, 4/6, and P of F is 3/6. We can also find the intersection of the two events was 4, 6, and so the probability of the intersection E and F is 2/6. And finally, we can check for independence, because we can look at P of E times P of F, 4, 6 times 3, 6, which happens to be 1/3, which is the same as P of E and F. So in this case, E and F are independent events. But let's define another event. What if we call G the event that the roll is greater than 3. So it's just 4, 5, 6. Now we can see that G is contained in E. So they're clearly not independent. I want you to think about why that is for a second. Why is it the case that if one event is contained in the other, they're definitely not independent? That's because if one of them occurs, if G occurs, then E will definitely occur. So they clearly have some influence on each other. All right, let's think about F and G now. Are they independent? Well, we can check the official definition, or we can use the alternate definition. Let's think about the probability of F given G. So G is the outcomes 4, 5, and 6. So if we know that G has occurred, we know that the roll is 4, 5, or 6, then the probability of F, the probability of it being even, is just, well, there's 2 out of those 3 things, 4 and 6 are even, which is not equal to the unconditional probability of F. So in this case, they're not independent. We see here that the probability of F given G is greater than the probability of F. So if G happens, that makes F more likely to occur. Or we could actually go the other direction. We could calculate P of G given F, and it turns out to be greater than the probability of G, which means that F makes G more likely to occur as well. So my question for you is, does this hold in general? Is it always the case that if one event makes the other more likely, the opposite will also be true? Will both events make each other more likely, or could we have that influence go in different directions? We'll actually explore this a little bit more in the first tutorial assignment next week. All right. Lastly, I want to talk about 2 rules to manipulate probabilities: the partition rule, which is also known as the law of total probability, and Bayes' rule. So we say that events A1 through AK form a partition of a sample space S if the following 2 conditions hold. First of all, we have to have those events be mutually exclusive. So AI intersect AJ is the empty set, and also they have to cover the entire sample space. So if we union them all together, we get the sample space. An obvious example would be any event and its complement that makes a partition of size 2, because together they cover the whole sample space. So let's now think about any event E on a sample space and a partition of that same sample space, A1 through AK. And here's a picture. Let's pick a sample space here and a partition of size 5, just a bunch of random puzzle pieces that kind of fit together. We can always write any event E as the union of several pieces, each of which are intersecting those parts of the partition. So we're kind of carving up the event E along the lines of that partition. And then if we want to calculate the probability of E, we can use the fact that these pieces are now mutually exclusive. So we can look at the sum of the probability of AI intersect E for all pieces of that partition, and that's by that additivity axiom. Finally, we can apply the product rule to each of the pieces of that sum and get the probability of being in the piece of the partition times the probability of E conditional on being in that piece of the partition. So this gives us a really nice way to find the probability of a complicated event E by splitting it up into different pieces and using conditional information that we might have. Next, we have Bayes' rule, which is going to look deceptively simple, but it's a really powerful tool. And here's where we're looking for the probability of F given E. Well, we start with the definition, probability of E of F divided by probability of E, and then we apply the product rule to the top, but in the opposite direction. Notice here we're conditioning E given F. And in the denominator, we apply the law of total probability, or the partition rule, using the partition F and F complement. So if you look at this, notice that we wanted a probability of F given E, and we've written it in terms of probabilities of E given F and E given F complement. So Bayes' rule is really useful when we have conditional information in one direction, but we really want it in the other direction. We want to reverse the direction of that conditioning. I'm going to illustrate both of these rules with an example. So imagine that we have a blood test for a certain disease and it has a 1% false positive rate. So a false positive means that the test says the disease is present, even though it's not. So conditional on it not being present. And similarly, a 0.5% false negative rate, again, a false negative would be, it reports there's no disease if it actually is present in that individual. And we'll say an estimated 0.3% of the population has this disease. So we might be interested in a couple of things. First of all, what is the probability of a randomly selected person from this population testing positive? And second of all, if a random person does test positive, how worried should they be? What's the probability they actually have the disease given that they tested positive for it? Think about this and see if you can come up with a solution on your own before watching further. Let's start off by letting T equal the event that the test is positive and D equaling the event that the disease is present. And we want to think about what we're given in the question. We have these 3 numbers, 1%, 0.5%, and 0.3%. How did they relate to probabilities involving these events, T and D? Well, first of all, the easiest one is that P of D is that 0.3%, because probability of having the disease in a randomly selected person is that 0.3%. Next, we want to think about our false positive rate. So the false positive rate of 1% represents the probability of testing positive given that you don't have the disease. And similarly, the probability of testing negative given that you do have the disease, that's the false negative rate of 0.005. So now to answer the questions, for part A, we want the probability of testing positive. So we can use the partition rule, and that's going to be P of D times probability of T given D, plus the probability of D complement times P of T given D complement, and that gives us 0.12955. For part B, we wanted the probability of having the disease given you tested positive. So here's where Bayes' rule comes into play. We look at the probability of D times the probability of T given D and divide it all by P of D. And that gives us 0.2304. So I want you to think about why that number is so low, right? This test sounded like it was pretty accurate. It only had a 1% false positive rate and a 0.5% false negative rate. Why does a positive test only tell you you have a 23% chance of getting the disease? And pause now and think why that might be the case. If you've unpaused now, part of it has to do with the fact that the disease is so rare, right? We have 0.3% of the population actually having the disease, which means that out of all those tests that occur, a lot of them, actually more than half of them, about 3/4 of them, are false positives. The false positives are kind of overwhelming the true positives. And so having a positive test result doesn't guarantee that you have the disease, even though it sounds like the test is really, really accurate. Because again, those false positives are so numerous compared to the true positives. All right, that is everything for this video. I will see you soon.